Now, finally, in our conceptual framework, we're going to talk about voltage drops in series and parallel circuits. Uh, First of all, what the heck is delta V? We got to remember, perhaps from that mnemonic that we learned, delta V, volt U over charge, is simply delta U, the change in potential energy, electric potential in this case, per unit charge. Delta U over Q, volt U over charge. It's the total voltage drop is simply the voltage drop across the power supply or the battery. There's our delta V total. Now, the voltage drop or the voltage difference across the power supply is often referred to as the EMF. And that stands for electromotive, meaning pushing electrons, force. But it is not a force. It's called electromotive force for historical reasons, but it's not a force. It is given this symbol curly E, to distinguish it from other delta V's. When we get to capacitors, or if you've already done capacitors in AP, you know that when you charge up a capacitor, the delta V across it changes. This is not really true with batteries or power supplies. Putting charge through them does not change the delta V across them appreciably. By the way, delta V across an ideal wire, if it's an ideal wire, again, has no resistance, it will have no voltage drop across it. Electrons don't lose any energy as they go through an ideal wire. So let's take a look at our water analogy here and see how this can help us. What we have right here is a pump that is producing 30 pounds per square inch at the outflow point, and we can just arbitrarily set, okay, it goes in at 0 psi. You can really set 0 wherever you want. We actually do that with atmospheric pressure. If your tires are empty, they're at atmospheric pressure, but we call that 0 psi gauge pressure. So we'll just call that 0 psi down there. Now, how is the pressure going to change? Now, when we go through this part right here is a frictionless pipe. It's not losing any energy. Pressure is actually a form of energy. Right here, the pressure is still going to be 30 psi. Pressure is not lost in this frictionless part of the pipe, but it then goes through this gravel-filled part, and the gravel-filled part does turn pressure into thermal energy. So some pressure is lost, and this is true in plumbing, in fact. You lose some pressure when you go through any kind of resistance to the flow of water. So I'm just going to arbitrarily say here the delta pressure is equal to negative 20 psi. And I'm just making up some numbers here. And so what's going to happen in here, once their delta P is negative 20, some people say, well, they just call it positive 20. They don't worry about the sign. But it's dropping down by 20, and that leaves what right here? It'll be 10 psi in here. So the pressure in this part is 10 psi, and notice that we don't lose any pressure as we go from this point to this point. Pressure is the same everywhere in this frictionless part of the pipe. But we're going to now go through this pipe right there. Now, this pipe is wider than the pipe we had before. Do you think we'll lose more pressure or less pressure through this wider pipe? A wider pipe is like a lower amount of resistance, so you might guess we're going to lose less pressure. So I'm just going to arbitrarily say, well, why don't we have delta P for this part is negative 4 psi. So it drops down here, and when we get through here, the pressure is, all that we have left is 6 psi. And you might guess, well, how much do we have to lose to get over here? Over here, it's back to 0. So yeah, we do have to lose. Delta P is equal to negative 6 psi. Now, I should say that many times when people are analyzing these circuits, they'll just say the delta P here, or the pressure change here is 20. They'll just neglect the fact that it's negative, or they'll just say the pressure drops by 20. It'd be redundant to say it drops by negative 20. It does change by negative 20. We always lose pressure as we're going through gravel-filled pipes or resistances. So let's go over to our our actual circuitry here and see what's going on. Now, the first question I got for you is, what's Itotal? Before we go on, let's go ahead and figure out what Itotal is. Now, we have a 30-volt battery. It's a 30-volt difference across that, just like it's a 30 psi difference across our pump right here. It's a 30-volt difference across the battery. What's Itotal? Well, what is the R total? R total is 10 plus 2 plus 3 because they're in series. So that's 15 ohms total experienced by the battery. I total is just delta V total over R total. Notice that the subscripts are the same, and that's going to be, in this case, 30 over 15, 30 volts over 15 ohms, and then we see that that is equal to 2 amperes. So I've got 2 amperes going out there. How much is coming out there? Well, if you understand the currents in series, you know that's 2 amperes too. This is 2 amperes there, and 2 amperes have to be going back into the battery, 2 coulombs per second. So what are my delta V's? Now you'll see where I got these pressure numbers. What is the delta V across this one? Well, the delta V's across each individual resistance can be calculated as such. Delta V, just using Ohm's law, delta V1 is I1, the current through resistor 1, times R1, the resistance of resistor 1. So that is 2 amperes times 10 ohms. And that is 20 volts. Now it is negative 20. It's dropping by 20. So I'm going to put that up here. Delta V equals negative 20 volts. Just like this delta P is negative 20 psi. Some people will say, well, the voltage change, it drops by 20, so they might just list it as 20 like I have here. Delta V2, what's that going to be? Well, it's going to be I2 times R2. Notice the subscripts are the same. And again, I have that as 2 amps times, in this case, 2 ohms. That gives me 4 volts. Again, delta V is negative 4 volts. It's dropping by 4. And delta V3, it's gotta get us back to 0 volts here. This is 30 volts at that terminal. It's got to be 0 volts at this terminal. So delta V3 is going to be I3 times R3, and that gives me 2 amps times, that is 3 ohms, and of course that gives me 6 volts. Delta V across this one drops by 6 volts, negative 6 volts right there. And then I'm going to end up back at 0. Now, notice that for series circuits, delta V total must equal the sum of the individual voltage drops across the resistors. So for series circuits, delta V total must equal the sum of the individual voltage drops. So if we start with 30 pounds per square inch here, we got to get back to 0, so it's got to drop down by that total amount as we go through those gravel-filled pipes. Similarly, the total delta V, 30 volts, it's got to drop down by 30 to get back to there, so all these voltage drops have to add to 30 as well. Now, the largest potential energy loss, in other words, the largest delta V, because delta V is equal to delta U, potential energy per Q. So the largest delta V must be across the greatest resistance. So, and as you can see here, we have in fact lost the greatest amount of voltage through our 10 ohm resistor here. So notice the biggest voltage drop is across the 10 ohm. And that's the smallest voltage drop is across our smallest resistor. So that makes a lot of sense. The narrowest pipe, which corresponds to the greatest resistance, will actually give us the biggest voltage drop in series.